First semester calculus is really concerned with two basic problems. One of them is the slope of a tangent line, and we developed the idea of the derivative. We discovered that there were lots of things that we could do with a derivative besides just finding the slope of a tangent line. And the second big question is the area under a curve. And as was the case with the slope of a tangent line, we're going to discover that when we know how to figure out areas under curves, we'll be able to do a lot of other things. So here's the basic problem. We've got the graph of a function, y equals x squared plus 1. The graph is not a line, which means that the area here is not an area we can compute using sort of standard shapes that we know about, at least not exactly. Right? If this were a triangle, we could do it. If it were a rectangle, we could do it. It's a curve. So we're going to start off with a mechanism to approximate this area. And what we're going to do is we're going to use rectangles. So here's a picture. We take these 3 points, 0, 1, 1, 2, and 2, 5, and we draw rectangles under the curve where the height is given by this left-hand endpoint. So here you've got this rectangle of length 1. Okay, the height is 1. You've got this rectangle of length 1. The height is 2. And then you've got this rectangle of length 1, and its height is 5. Notice that we've done is broken up this interval between 0 to 3 into 3 even pieces. And at each case, the height of the rectangle is given by the function value at the left-hand endpoint. Now, if we look at the area estimate we get here, this height is 1, this length is 1. 1 times 1 is the area of this rectangle. This length is 1. This height is 2. 1 times 2 is the area of this rectangle. This length is 1. This height is 5. 1 times 5 is the area of this rectangle. So 1 plus 2 plus 5 equals 8 is our area estimate. Now, if we look at this picture, we can see that that area estimate is too small. We've missed these regions. We might just as well have drawn rectangles, but used the other endpoint. So same idea, broken up into 1, 2, 3 pieces. This time, however, we draw rectangles based on the height at the right-hand side. And length 1, height 2, length 1, height 5, length 1, height 10. Our estimate, 1 times 2, 1 times 5, 1 times 10, and 2 plus 5 plus 10 is 17. And this is too big, but what you can say for sure is the area, whatever it is somewhere between 8 and 17. Now, to do even better, what we should do is break up this interval into more pieces. So we're going to do the same thing. This time, we're breaking it up into 6 pieces. This length is 3. 6 pieces. Each one of these lengths is 1/2. Okay, so each base now is 1/2. Height is at the left-hand endpoint. So that first rectangle, length of the base is 1/2. Height is 1. So we get 1/2 times 1. And then this piece is going to be length of the base is 1/2. Height is 5/4, which is the function value at 1/2. So we're going to pick up 1/2 times 5/4, and now we do the same thing for each one of these rectangles. And by the time we're done, we end up with an estimate of 9.875, which you can see is a better estimate than 8. We're missing less area here than we were up here. We could do the same thing with right-hand endpoints. And we would get an estimate, again here, length a half, height this time is 5/4. So this first rectangle is 1 half times 5/4. This second rectangle is 1/2 times 2. We go through that whole mess and we get 14.375. So our answer is somewhere between 9.85 and 14.375. And now to do even better, we should use more rectangles, which nobody would do by hand. So I'm going to now show you what that looks like on a computer. So now what you see in front of you is that same approximation we made previously using right-hand endpoints of rectangles. And you can see that the estimate was 14.375, which is too big. If we scroll down, we've also got an estimate here, which was the left-hand rectangles, 9.85, which was too small. So what we're going to do now is we're going to increase the number of rectangles, and we're going to do it fairly dramatically, 10 times as many rectangles. And we get the following picture. Now, if you look carefully, you can see that this is a much better estimate. It's still too big. You can see little pieces of the rectangle protruding above, but it's much closer to whatever the area is, and you'll see that the answer that came out is 12.2263. If we do the same thing with our left-handed rectangles, which gave us too small an answer, again, you can see it's a much better estimate, and we're getting 11.7763. So just between the two of these things, too big, too small, the answer looks like it's probably around 12. What we'll do now is we'll increase dramatically again, 10 times as many. Now the picture is not going to look nearly as nice. Okay, it's very, very difficult to detect the rectangles at all here. And visually, it looks like this is almost perfect. But mathematically, if we were to zoom this thing, you would see little tiny rectangles still protruding. We're getting 12.0225. And when we do this one at 600, we get 11.9775. Now, we're closing in on an answer, and that answer is looking closer and closer to 12. And one more time. Now, this time the graphics simply won't be able to handle this. And you'll notice it takes a while because the machine is chugging away. And what we're getting this time is 12.0023, which is too big. And when we do 6,000 down here, chugging away again, we get 11.9978. So at this point, the answer is looking a whole lot like it's about 12. Now, we will learn for particularly nice functions how to find the answer exactly. But there are lots of functions out there that people care about where you can't. So computers are very useful for doing these sorts of calculations, and they're based on these same sorts of ideas. Now let's discuss this method for general functions. By the way, the name of the estimate that we are making by adding up these rectangles is a Riemann sum. And these Riemann sums are the things that converge to the area. So let's take a look at a general situation here. This time our function is y equals f of x. Our interval isn't 0, 3 anymore, it's a to b. And we're going to break up, to begin with, this thing into 6 pieces. So the length of the interval is b minus a. There are 6 equal pieces, so each little length of the base, which I'm going to call delta x, is b minus a over 6. If you look at the points, here's a. You move delta x, a plus delta x, a plus 2 delta x, x plus 3, a plus 4 delta x, a plus 5 delta x, and b. Now, we're going to draw here the left-hand endpoint estimate. Now, we saw both the left-hand endpoint estimate and the right-hand endpoint estimate ended up converging to the area. So if there actually is an area, it doesn't matter which one you use. So we'll do this for left-hand endpoints. Now, what we can see is the area we're going to get is this height, f of a times delta x. This height, which is f of a plus delta x times delta x, etc. We end up with f of a delta x, f of a plus x times delta x, f of a plus 2 delta x times delta x, all the way up to this. And this is our Riemann sum when we break this thing up into 6 pieces. Now, what if we break it up into n pieces? Well, the 6 just changes to an n, so it's the length of the interval divided by as many pieces as you're going to break it up. This formula ends up looking just about the same, only instead of going out to 5, we go out to n minus 1 of those. And now one of the things that people often do here is you can see there's a delta x in each one of these terms. Just factor it out. And now finally, what is the area? The area is the limit as n goes to infinity of this mess. And that is our definition of area. Let's look at a problem that at first sight does not seem to be related to what we've just been doing. A car travels along a straight highway all afternoon. At 1 p.m. the car's velocity is 50 miles per hour. At 1:30 its velocity is 60. At 2 its velocity is 60. And at 2:30 its velocity is 44 miles per hour. Estimate the distance traveled by the car between 1 p.m. and 3 p.m. For constant velocity, distance is velocity times time. So an estimate we might make is to assume that the car is traveling at a constant velocity during each of these half-hour periods. And we might as well take the velocity at the start of the period as that constant velocity. So the estimate we're going to get is 50 miles per hour for the first half hour, 60 miles per hour for the second half hour, 60 for the next half hour, and finally 44 for the last half hour. And when we do that, we get 50 times a half is 25 miles, 60 times a half is 30, 60 times a half is 30, 44 times a half is 22, or 107 miles is our estimate. Now let's look at what really happened. Here's a graph of a possible velocity function, and here are these points that we have just used. At 1 o'clock, 50 miles an hour. At 1.5, which is 130 in hours, 60, etc. What is this estimate? What we can see really happened is this. We have half-hour periods, and we have velocities at the beginning of each of these. This calculation is actually just the sum of these 4 areas. This is a Riemann sum. And it's a Riemann sum using left-hand endpoints. It estimates the area under the velocity curve. And since Riemann sums converge to areas under curves, we are led to the conclusion that the area under the velocity curve between t equals a and t equals b is the distance the object travels during that time period.